Okay, let us start. Meanwhile, other will join. So my name is Varnit Kapoor, and I'll be taking up this tutorial session for the course CFD using FVM. So let me share my screen. Okay, I think my screen is visible. All right. All right. So we were discussing about the discretization in our previous lecture week of on the finite volume method, and we dealt with the discretization of 1D diffusion equation. Okay. And then we did one question as well. Right. Uh, Nandita, am I audible? Hello.
Yes, yes, yes.
Okay. All right. Okay. So I have just started with the tutorial. So, okay. So my name is Varnit Kapoor, and I'll be taking up this tutorial. So let me start. So in the previous lecture, as I was saying, we have discussed about the discretization of 1D diffusion equation and using the finite volume scheme. And then we did some questions. And we'll start with today with few questions, and then we'll do the discretization of 2D diffusion equations uh, with the boundary conditions, uh, Neumann, Dirichlet, as well as mixed kind of boundary conditions. Okay. All right. So let us start. So I'll just write down one question first. Question says that there is a large plate of thickness L is equal to 2 centimeter. L is equal to 2 centimeter with constant thermal conductivity thermal conductivity of K is equal to 0.5 watt per meter per Kelvin, and uniform heat generation is happening. Uniform heat generation Q is equal to 1000 kilowatt per meter square. 1000 kilowatt per meter cube, sorry. 1000 kilowatt per meter cube. The faces A and B are at the faces A and B are at temperature of 100 degrees Celsius, 100 degrees Celsius, and 200 degrees Celsius, respectively. Assuming faces, assuming that dimension in the y and z direction y and z direction are so large that temperature gradients are significant in X direction only. Only, and we have to calculate the steady state temperature distribution. State temperature distribution. The governing equation is like this: d of dx a dt of dx plus q equal to 0. And the figure will be like this. So suppose you have a plate. And these are the z, y, and x directions. And this is L, this is L, this is point A, the temperature is TA, and this is point B, the temperature is TB. This is okay, like this. So we have done in our previous lecture about method of solution where it was demonstrated using a simple grid and where the domain was divided into 5 control volumes. Okay. So here, if we take a spacing of dx is 0.004 meter, and as a unit area is considered in the YZ plane, because it is given that you have to assume dimension in YZ are so large that temperature gradients are significant only in the X direction. All right. So what we will do, we have again only the X direction in the length L. So let us solve this solution. Solution for this. So again, I'll make a uniform distribution of it. This is the temperature at point A TA, and this is the temperature at point TB. Okay. And I'll consider 5 nodes here. Node 1, node 2, node 3, node 4. I guess these are not equal. So let us 2, 3, 4. So suppose you have point of concentration is this as point P if we consider. This is point P. So it is west node as well as east node. So if I take a control volume of this, the control volume with this is a P, this is phase E, phase is east phase, this is west phase, and this is these are the west and east nodes. The corresponding west and east nodes, capital W and capital E for this particular control volume. And the elemental EX of control volume of the control volume. So first we will apply the integration on the governing equation. Right. So long plate L is equal to 2 centimeter, which is given in the question. Okay. So if you divide in 5 equal parts, divide someone has joined. Mohannapi, I'm audible. Are you connected?
Yes, sir.
Okay. So I've just started with the question. Okay. So we have a large plate, and it's a one-dimensional kind of question where the governing equation is like this. Okay. All right. It's a diffusion equation with some heat generation source, uniform heat generation source, and temperatures T and TB are maintained for this. And again, we are solving it using the finite volume scheme. I just started. So if you see, we have divided into 5 different control volumes. Divide the domain in 5 equal control volumes. Or I'll write control volumes first. Okay, 5 equal control volumes. We have the equation and perform the integration. So if there are 5 equal control volume, therefore dx will be L over n. The length is 2 centimeter into 10 to the power of minus 2 over 5. So that will come out to be 0.004 in the meters. Your spacing dx. Now we will perform the integration, formal integration of the governing equation. Of governing equation over control volume. Over control volume. All right. So equation is E by dx of k dd by dx dv plus LV q dv equal to 0. Okay. Now, if you see this, the first term, we have done same kind of thing in our previous tutorial. And the second term, integral, is the source term of equation, which is evaluated by calculating the average heat generation source, that is S del V, okay, within each control volume. So this we have done in our previous tutorial. So how you will do? By GDT you will apply first, and then you will, for east and west phase, you will write. So it will be like Ka dt by dx of east minus Ka dt by dx of west plus the integration of this will be Q del V equal to 0. Q del V equal to integration of dV, because Q is constant, uniform heat generation source. So if I write the further discretization, Ka of east, you can say T east minus Tp upon del x. So I've notated with dx, so I'll write with dx. Dx minus Ka west, that will be Tp minus T west on dx or del x plus Q, and this delta V can also be written as A into, where's John? And this delta V can be written as area into dx, area into control volume. Okay, that is equal to 0. Okay. Now you will take out the P terms separately. West node term separately, east node term separately, and the source term separately. So first I'll take out the p terms. This p term is here, p term is here. So that will be TP, okay, east, A east plus K west over delta X. Then there will be east term, K east, A east, okay, that will be by dx, and that is T east plus K west, A west by dx, that is really T west node plus QA dx plus QA dx. That is a kind of, again, a kind of a problem. APTP is equal to AW TW plus AE TE plus some source term SU. Some source term SU. And this is the equation for the internal nodes. Those are 2, 3, 4. 2, 3, 4 in the given figure are the internal nodes, because I have divided into 5 equal control volumes. So what you can say, AP is, first I write A west is, A west is KA, or let me write, because it's a uniform slab, you can say that K east, K west is nothing but K. A east, A west face is equal to A. Okay? So you can say AW can be written as KA by delta X. A east can be written as KA by delta X or dx. And AP will be written as AW plus A east minus the source term S, whatever the source term is, SP, which is 0, plus SU, which is, just you can write it like this also. Simple. Okay. It is just summation of both. Now this is the control volumes. This is valid for internal nodes. Valid for internal nodes. Those are 2, 3, 2, 3, and 4. And the boundary nodes will be given a special treatment, because for a node 1, if you observe, there is no west node for it, and for a node 5, there is no east node for it. Okay. Similar way, we will give a special treatment to the gene, which we have done in our last lecture as well. So we'll write any doubts so far to anyone?
No, sir.
No. Okay. All right. So yeah. So for node 1, internal node, boundary node, 1, if I have, then there will be a special treatment, because KA dt by dx of east minus KA dt by dx of west plus Q delta V equal to 0. Now east it has, so KA into TE minus TP by del X minus KA. Now it has TP, but it does not have west node. Okay, it does not have west node. So it will be TP minus TA upon del x by 2. Del x by 2 plus QA del x equal to 0. If you observe, that will be KA. Now take out the first of TP. Oh, first of all, you will take out the TP, then T
Excuse me,
east
sir.
and T west. Yes, any doubts?
Yes, sir. Why it is
Yeah.
TP minus TA? Why it is not TP minus TW?
No, we are dealing with the boundary node, na. So if you see the boundary node 1, this is your boundary node 1. So it does
Okay.
not have a west face. It is absent for it. So that is why I've taken TA. We have done this special treatment in the last tutorial as well. So when you are TP minus TA, then spacing between the two will be dx by 2.
Right, sir.
If you observe, the spacing here is dx by 2. Are you getting this point?
Yes, yes.
For internal nodes, I have already framed the equation. All right. Now, TP, we take out the components. TP Ka by dx plus 2Ka by dx SCP. Then T east will be Ka by dx. Ta will be 2Ka by dx plus Qa dx. Plus Qa dx. Okay. Similarly, for the node 5 also we can write this equation. Okay. So it is something like Tp Tka by dx is equal to Ta to Ka by dx plus T east Ka by dx plus Qa dx. This is your equation for node 1, boundary node 1. This was your equation for internal nodes. Internal nodes. Similarly, for boundary node 5 also you can write the equation. Boundary of boundary node 5. So again, it does not have a east node this time, so it will be just boundary B. So Ka dt by dx of east minus Ka dt by dx of west plus okay, plus Q delta V equal to 0. So K A into TB minus TP over dx by 2 minus Ka TP minus T west, sorry, over dx plus Qa dx equal to, again, if you take out for Tp first, Tp 2Ka by dx plus Ka by dx is equal to T west Ka by dx plus Tb 2Ka by dx plus Qa dx. That will be 3Ka by dx is equal to T west Ka by dx plus 2Tb Ka by dx plus Qa dx. So this is your equation for boundary node 5. Now you have all the values with you. You can put all the values for all the 5 equations. Boundary node 1, boundary node 2, 3, 4 is this. Boundary node 1 is this. Boundary node 5 is this. You have all the boundary conditions given in the question. Put the values and you will get the answers for the same. Okay, and you will form a matrix which will be a 5 cross 5 matrix, then a vector of temperatures, and on the right hand side, all the constants will come. Okay. So if I write this in a matrix form, of course, so my solution will be like this. After putting all the values, or let me write first thing. After putting all the values from question, or you can write given, or putting all the values given, you can say that will be 375 minus 125, 0, 0, 0. Okay. Then minus 125, 250. That will be minus 125, 0, 0. Then 0, minus 125. So first row indicates the node 1. Second, third, and fourth row will indicate the node internal nodes 2, 3, 4. And last row will indicate the node boundary node 5. Minus 125, 250, 250. Again, minus 125, 0, 0, 0. Minus 125, 250, minus 125. And finally, 0, 0, 0, minus 125, and 375. This is T1, this is T2, this is T3, this is T4, this is T5. The temperature values which you want. And on the right hand side, you will be remain with 29,000, then 4,000, 4,000, 4,000, and final is 54,000. So this is node 1. This is node 5. And these are internal nodes. Node 2, 3. Okay. Now you will solve this equation using any of the iterative schemes, iterative solvers, which you make, and you'll finally get the temperature values after solving. You'll get the temperature values as T1, T2, T3, T4, T5. The values will come out to be 150. You can compare when you will, if you want to make a solver and get the values. 254, 258, and 230. These are the temperature values which are asked in the question. Calculate the steady temperature distribution. Also, you can integrate the given equation and get the analytical solution as well and compare. So what kind of graph you will get will be something like, I'll show you. The kind of graph you will get will be so y-axis represent the temperature, degree Celsius, and it represents the distance in meter. So starting from 0, the temperature at A was maintained at 100 degrees Celsius. 100 degrees Celsius, and temperature at B is maintained at, I guess, 200. Let me see, 200 degrees Celsius. Okay. temperature B is maintained at 200, or somewhere around 200 degrees Celsius. So if you see the temperature values which have come from this, it's from, so there is a maximum value of 258 as well. Maximum value of 258 as well. So that means somewhere it is 200 here, and somewhere here it will be 258 as well. 258. Graph, if you will see and plot, try to plot it out. So maximum value come here, and it will go till up to domain. So domain length is from 0 to 2 centimeter. This is 2 centimeter. Okay. All right. So what you will find that this is a exact solution, and at some points you will find the values, 5 values, at 5 different values you will find, which you have got T1, T2, T3, T4, T5. Okay. So third is value is this, fourth is this, fifth is 258. That is the maximum value. Okay. And these are the numerical values in the red. After solving this equations, and this is the exact values for analytical. I guess exact value, find one exact values. I hope this question is clear, or any doubts in this.
No, sir.
No doubts. What about Lakshmi? Do you have any doubts?
No, sir.
No doubts? Okay. All right. I will give you guys one question that you guys must solve. At least frame the equations. I'll write down the question. Question states like, there is a cooling of a circular fin happening. Cooling of a circular fin by means of convective heat transfer along its length. Convection give rise to a temperature dependent heat loss or heat sink in the governing equation. Okay. So the always make sure that. And cylindrical fin has a uniform cross section area. Cylindrical fin has a uniform cross section area A. The base is at temperature of 100 degrees Celsius. (100 degrees Celsius). Okay. And end is insulated. This is TB base, and end of the fin insulated. End is insulated. Fin is exposed to an ambient temperature of 20 degrees Celsius. One dimensional heat transfer is happening using the governing equation d by dx Ka dt by dx minus HP T minus T infinite is equal to 0. So this is T infinity, ambient temperature, where H is the convective heat transfer coefficient, H is convective heat transfer coefficient. Okay. P is the parameter. Perimeter. K is the thermal conductivity of material. Thermal conductivity of material. And T infinity is the ambient temperature. You need to calculate the temperature distribution. Temperature distribution along the fin. And you can compare with the analytical solution as well. And the equation is like T minus T infinity for the fin. If you have been taught in heat transfer subject, cos h n into L minus x over cos of hyperbolic NL, where n square is HP by Ka, n square HP by Ka. L is the length of fin length. X is the distance along the fin. Okay. And L is given to be 1 meter. HP by Ka is given to be 25 m-2, and Ka is constant. The figure is like this. If you want the cylindrical fin, this is material TB, this is T ambient, this is insulated, this is insulated. All right, I'll zoom it out. Still after zooming out, question is, I guess figure you understood. There is no need for the figure, but still all these values. Is it visible? Mohanna Priya? Mohanna, is that visible? Okay. We'll just try it out. I'll give you a few minutes. Nikita, I'm audible? Nikita, are you there in the session? Can you please confirm? Okay, please solve this question. Okay, anyone has solved? Priya, have you solved this? Or shall I solve this?
I'm waiting for the solutions, sir. Actually, this is a second order differential equation. That's why.
So we have done this question just about.
That's the first order, isn't it?
The same equation was this d by dx of k dt by dx. See the governing equation. It's the same equation.
Okay.
Nothing changed.
Right.
All right, let us solve.
Right.
Solution. Okay. So if you see that the governing equation here, this equation d by dx k dt by dx minus hpt minus t infinity. So contains a sink term that is hpt minus t infinity. Convective sink term, which is convective heat flux, which is nothing but a function of local temperature T. So as before we did in the first step in solving the problem by the finite volume method is used to set up a grid first. Then we use a uniform grid and divide the length into equal 5 control volumes. Okay. So again, I'll make 5 control volumes. Again, one dimensional because it's a d by dx only it's given. So again, I'll divide in 5 control volumes. So this is TB base. And here it is insulated. So Q is equal to 0 is given here. Okay. I'll divide in 5, 1, 2, 3, 4, and 5. Okay. So again, if I take this as a point of concentration as P, and make a control volume. This is a point of concentration. So this will be the S node. This will be the east node for it. This is your dx for delta. Okay. And this will be your dx over. Okay. Now it's in 5 control volumes. So L is equal to, sorry, dx is equal to L over N. The length is given to be how much in the question? Length is going to be 1 meter. Okay, 1 meter. 1 over 5. So that is 0.2 meter is the spacing. 0.2 meter spacing. Okay. So the given equation, because we know this relation, given equation HPT minus T infinity. Okay. And we know that N square is nothing but HP over KA. Since N square is HP over KA, so that this implies HP is nothing but N square K. Like this also we can write. Okay. Is it fine? And Ka is a constant value. Ka is a constant value. Is given in the question. This is constant. So our given equation d by dx of a dt by dx can be written as minus n square t minus t infinity equal to 0, where n square is nothing but hp over ka. Now you will integrate it over a control volume. Integrate it over a control volume. Integrate over a control volume. See what you will get again for the internal nodes, you know, a dt by dx. So I have taken n square into ka. One thing I have, this will be dV after integration, and this will be also dV after integration, that is equal to 0. And this was n square into Ka was a constant. So this K and this K also I can eliminate from both this thing. And now this can be written as A dt by dx of east minus A dt by dx of west face, because this is your east face, this is your west face, right? Minus n square Tp minus T infinity, because T is now Tp, point of concentration, into AdX. dV can be written as AdX. Again, for the internal nodes, you know that A T east minus Tp over dx, okay, minus A Tp minus west over dx minus n square Tp minus T infinity AdX equal to 0. So we can omit this A as well. A from here, A from here, A from here on the right hand side. And if we consider only the first P terms and put it all together, so what you will get? Tp into 1 by dx plus 1 by dx is equal to T west over 1 by dx plus T east over 1 by dx. Fine, plus it goes on the right hand side, that will be n square T. Okay, so let me write the Tp term here as well. I missed one term here. That will be 1 over dx plus 1 over dx plus one thing, n square right hand side plus n square dx, n square dx. Okay, and here it will be minus n square plus n square T infinity dx. Okay, all right. Now again, it is a form of an equation: APDP, AWW, AEs, TEs plus some source sum. All right. Now this is for the internal nodes. This equation is valid for internal nodes. Node 3n. Now we come to boundary node. Oh, I guess come to boundary node. Boundary node 1. Again, you will frame the same equation. So I'll not frame this time. I'll just write the equation. The equation will be like Te minus Tp over dx minus Tp minus T base, because the boundary node 1 has only the base wall temperature. No west node is absent there. Dx over 2 minus n square Tp minus T infinity equal to 0. This is boundary node 1. Similarly, boundary node 5, that will be similarly east node is not there and the flux is 0. So on the when you write k dt by dx ka east minus ka dt by dx west, but flux itself q is equal to Ka dt by dx of east, which is given to be 0 in the question. Given it is insulated. Given as insulated. Therefore, 0 minus dp minus the west node over dx minus n square dp minus d infinity dx equal to 0. This will be your equation for this form. And after getting all the 5 equations and put in the, if you see the previous matrix, that was also enough tridiagonal. You see minus 125, minus 125, minus 125. Then this was minus 125, minus 125, minus 1. And if you see the middle one, right, the rest all the values were 0. Similarly, this kind of matrix will also be formed. Matrix will be, you will get 20 minus 5, 0, 0, 0, then minus 5, 15, minus 5, 0, 0, 0, minus 5, 15, minus 5, 0, 0, 0, minus 5, 15, minus 5, 0, 0, 0, and minus 5 and 10. So this will be T1, T2, T3, T4, T5, and 1100, 100, 100, 100, 100. Again, if you observe this kind of a matrix, is nothing but the central main diagonal, this is your other diagonal, this is your third diagonal. Kind of again, tridiagonal kind of matrix. So after solving, using the Redis schemes in the solver, you will get T1, T2, T3, T4, T5 as 64.22, 36.91, 26.5, 22.6, 1.3. If you see, base temperature was 100, then temperature goes on decreasing, 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 decreasing up to insulation, whatever was the. Okay. And if you make a graph also, so you will observe the kind of graph it will be formed. Temperature distribution. This is distance. The graph will be something like starting from 100, it will go down like till somewhere up to 20. Okay, so this is a exact analytical solution. Some values will come out for numerical solution. Okay. Any doubts till here in this question? Mohanna Priya, is there any doubt?
No, sir.
Clear?
No, no doubts.
So you have solved the assignment for week up till week 3, week 4. Have you solved? Hello?
No, the year after we are going to solve. Assignment, isn't it?
So tell what assignment you have solved so far. I can't hear you. Hello? You hadn't solved any? You don't have any doubts so far in the assignments? Okay. If no doubts, now we will start with discretization of a 2D diffusion equation. So far we were doing 1D diffusion equations. Now we'll come to 2D diffusion equations. The heading will be, have you watched the lectures for week 4? Hello? Have you watched the professor's lectures? Discretization of 2D diffusion equation. Now, so far we have seen the 1D diffusion equation, solved a lot of questions. But what happens in the two-dimensional is that there is a cell, there's a diffusion term and a source term, suppose. Okay. So equation something looks like this: del of grad of phi plus some source term s phi, where del operator is I dou by dou x plus j dou by dou y. Okay. Now what you have is that you have a grid in 2 dimensions this time. So I'll frame a grid. Okay. So one more. So suppose all these are the directions in x and y, the 2D grid. This is y direction. This is x direction. Your cell control volume is a consideration is this P. Okay. So the west this is a control volume. So this is west, this is east, this is north, and this is south. And these are the faces: east face, north face, west face, and south face for this. And the spacing between them is like, so spacing for P to E, capital P to capital E, is like dx del x E del x E, and that will be del x W. This whole control volume with this del x. Okay. Then from south, so from here to here, it is del y s for south, and from here will be del y north. Okay. Alright. So we have defined our spacing. Any doubts in understanding the spacing part? This is del. Sorry. Any doubts in understanding this grid notations? Which term is which term? If you have any doubts, please tell me. Okay. Just give me a second. Please carefully observe the grid. Then I'll start with the discretization. Understand each and every term. Okay. So now we will first step is we will integrate the governing equation on the control volume. Integrate governing equation over control volume. So that is control volume. Our governing equation was EV plus control volume with some source term S5, PV equal to PV. Okay. Now this is your control surface this time. This part, let me take some another color. So this is your complete control surface. Control volume is a whole cell. This is a control surface of the control volume. Okay. Now, if you see, this can be written as summation of all the faces that is east, west, north, south, east, west, north, south, after applying the GDT, cross divergence theorem. Gamma of grad phi of all the faces of area of all the faces plus S phi del V equal to 0. Now you have east, west. So A east, if you want to write, that will be written as A east will be written as del Y plus J0, because if you see, this is the east face and it has del Y. This is del Y, and in the other direction it is of unit, whereas east face does not have any X. So in the I direction it has just del Y, whereas in the J direction it has nothing. Similarly, A west will be the minus of I del Y, minus of I del Y. Then A north will be, if you see the A north, this is A north, that will be del X, okay, in the J direction, Y direction. But in the I direction, it will be 0. So 0I plus del Y J, and A south will be minus of del Y J. Simple. And del V can be written as delta X into delta Y, because you have a control volume. whose x direction is this much and y direction is del y space. Okay. Yes,
Wait.
any doubts?
Yes, sir.
Huh.
Sir, how come it is east phase is expressed as I del y? Is it not I del x?
No, no. See, if I make a face in front of you, just a second. So if you have a control volume, this was a control volume. In the I direction, if you observe in a three-dimensional way, suppose this is a 1 unit. This is 1 unit.
Yes.
Okay. So what is the area of this face?
That is 1 unit.
No, area is 1 into del y.
Yes.
Area is 1 into del y, and that is in pointing in which direction?
I direction.
So I into del y into 1.
Okay.
But in j direction, it does not have any area, no? So that is 0. You got it?
Right. Yes, sir. Then what about north, sir?
So similarly, if you assume this is a north, this is a north face. Again,
Yes.
this is 1 unit. This is del x, which
Yes.
is pointing in which direction?
Yes.
J
J direction.
direction.
Yes.
So del y into j into 1.
So that should be del x, isn't it? So that length is del x and the unit
Oh,
is
correct. Yeah, thank you for the. It should be del x j.
yes.
I mistyped. Okay. All right. Okay. So we have written all the areas of the faces, east, west, north, and now we will put it. So if I want to write this term, gamma grad phi east, or gamma grad phi a east, because it was a summation for all the faces. So one by one, if I write the phase, so for the gamma grad phi, how I can write dou phi by dou x I in the east face plus gamma dou phi by dou x. So sorry, dou phi by dou y. Okay, because it's a grad operator. Grad operator is nothing but just I wrote in two-dimensional. Grad operator is this I d phi by d dou by dou x plus j dou by dou x. So that is I'm only writing gamma dou by dou x with the property phi over the grad plus gamma dou by dou y over the property east. So I'll write it again. So gamma grad phi east a east will be nothing but gamma dou phi by dou x, gamma dou phi by dou x in the east face plus gamma dou phi by dou y in the east face, because we are talking about east face only so far. Dot, what is the AE? AE is nothing but I del y. I del y. I del y. Okay. Now if you observe what it will be written, dot of this will be done with this part. Okay. I wrote I here and here it will be j. So I dot I is 1. Simple. So it will be dou phi by dou x, dou phi by dou x del y. Dou phi by dou x del y plus 0. So we can write gamma del y dou phi by dou x of east. Of east. Now similarly for west will be, it is just negative sign. Gamma grad phi of west dot a west will be nothing but gamma del y dou phi by dou x of west face. Now for the north face, how we will write gamma grad phi north a north will be nothing but gamma. You write for both the direction first. Gamma I dou phi by dou x north plus gamma I dou gamma j dou phi by dou y, correct? Because gamma is operator for both x and y direction in north, and that will be dot product with an is how much? An is this del xj. We will write del x j. The dot of j will be with this, and this. So it will be gamma del x dou phi by dou y in north. Okay, dou phi by dou x. And similarly, south will be just sign opposite. South the smallest, that will be minus of gamma del x dou phi by dou y. Any doubts in understanding this? Simple dot product, because our Gauss divergence theorem says that del dot of any function with control volume is nothing but f dot n cap into integral over dA, that we have discussed multiple times. So this is just a dot product of both the things, which I am doing. Any doubts? Mona Priya, please respond with yes or no.
Uh, no doubt, sir. Sir, I'm
No
not
doubts?
Mona Priya. Mona Priya is my daughter. I'm in her ID. I'm Anand actually.
Acha,
My
what
name
is
is
your name?
Anand. My name is Anand. I enter in my
Acha,
daughter's
okay.
ID, Mona Priya. I'm
Okay,
Anand.
okay. Anand. Okay, thank you for letting me know.
Correct.
Okay. So you can even change your name, I think, here. If I remember that, if you go in people and maybe you can change your participant name or before entering the whatever name is there. Anyways, now for the source term, we will assume the linear source model as we have done in our previous tutorials also. So for source term, we will assume linear source model, that is nothing but S phi will be written as S, the constant value plus SP, the property phi p, SP phi p. Now we will put all the values what we have got in our equation number 1. Let us say this is our equation number. Put all the values here for all the phases and the source term. Put all above values in equation 1. When you will put all the values, you will get gamma E del Y dou phi by dou X on the east phase minus gamma W del Y dou phi by dou X on the west phase plus gamma N del X dou phi by dou Y on the north phase minus gamma N del X dou phi by dou Y on the south phase plus the linear source term assumption is P phi P into del X del Y, because delta V was del X del Y. Okay. I hope this is clear. Now we will discretize each and every term as we did for east phase, west phase, north phase, and south phase. Let us discretize. So, Anand, what do you do? Basically, you are a working professional or you are pursuing your PhD.
So I completed my PhD. I'm a pure experimentalist. I did my PhD in IIT Kanpur. Now I have a little passion towards this one, what is it, computational fluid dynamics. So my friends are working in computational fluid dynamics laboratory, and then I went there and saw that a little exposure to that. So on my own interest, I'm doing that.
Okay, great, great, great. So your PhD was in like which? What
Uh,
was your PhD in?
Say in aerodynamics, actually, I did it in flat plate. That is flow over an flat plate. That is
Flat.
yes, actually, the airfoil is modeled as a flat plate. I followed Arena Muller as the basic paper.
Okay. So it was more of a computational work. or
No,
experimental?
I completed in 2016. I'm working in Shastra University. So as on my own interest, I took CFD as my paper. So parallelly, I'm
Okay.
learning as well as teaching the same.
Okay. Okay. Great. Okay. All right. So now each phase will be presented with gamma E del Y phi east minus phi P over dx, sorry, del x, we wrote now with the east phase del x E, phi E minus phi P over del x E. Right, that will I have del x E. Okay. Now, next term is gamma W del Y. Earlier, this term used to be in our 1D was used to be here. It was just A. But this time the A is divided in because each A is divided in two directions, I and J direction. Earlier, it was only one direction, so there was no point to discretize that A in two directions and separately write. That is why I explained this step for discretization of A here in both the directions. In both the directions. Okay. So step is similar, just the discretization happen. Now, coming to this. So this will be phi P minus phi W over del X W. Next term is gamma N del X phi north minus phi P over del X N minus gamma south del X phi P minus phi south over del X south plus the remaining source term SC plus SP phi P del X del Y equal to 0. Now I will take all the P terms together, east term together, west term together, and I'll write this. So if I take the P terms together, P, phi P, phi P all together, and if I write it, that will be phi P is gamma E del Y over del X E plus gamma west del Y over del X W plus gamma N del X over del Yn plus gamma S small s del X over del Ys. Sorry, one source term is also there. SP del X. This source term will also be there, no? SP del X del Y. This is your altogether phi P components equal to phi E components gamma E del Y over del X W, del X E, del X E plus phi W gamma W del Y over del X small w plus phi naught gamma naught del X over del Y naught plus phi south gamma S del X upon del Y south plus the remaining S constant source term. Okay. And any doubts in this? Just give me a second, please. Okay. Yeah. So we have written. So our equation is again a form of AP phi P is nothing but AW phi W plus AE phi E plus AN phi N plus AS phi S plus the remaining B source term, extra source term, which is there. Okay. Now this can also be written as AP phi P is nothing but summation of all the neighboring nodes NB, that is east, west, north, south, A and B, phi and B, plus the phi term. So this is your linear equation again. Simple linear algebraic equation has been formed. Okay. In 2 dimension. All right. I hope there is no doubt in here. Very simple way to deal with this. Now, if you see that discretization equation for flux linear terms are balancing the source terms. Okay. So what is happening in this equation? If you see this discretized equation is an equation for the flux if you have a source fluxes if you have. There is a linearity between the equation which is balanced by the source term from the neighboring terms. And if you see gamma and the gradient del phi by del x are following the linear assumptions or self-centroid values. Linear assumptions has been followed. And FVM is always a conservative form, irrespective of the mesh density. Okay, whatever the mesh density is, number of it is a very fine mesh or a coarse mesh. Also, if you see the Scarborough criteria, you see that it is following an equality or inequality way, which we have dealt in our previous tutorial. That number summation of neighboring points over the AP by the AP is less than equal to 1 and less than equal to 1 for all nodes and less than 1 for at least one node. Yeah, any doubts?
Yes, sir. This is something out of topic. How do you say a equation is conservative and non-conservative? It is said that in FVM, every equation is in the conservative form and every cells obey the conservation law of conservation. But in finite difference method, on a overall, when you are arriving at the solution, then only you will achieve the conservation. So in the meantime, if you are in the middle, definitely it won't be conserved. So that is what I came to know. But how do I identify the equation is in the conservative form and non-conservative form?
So see, I have answered this question in tutorial 2 as well. So if you write any equation, just a simple way to understand that it's a conservative form or not. Suppose you have an equation k dt by dx. This equation is a conservative form of equation is equal to 0. Why I am saying this? Because both the terms, when you will do a differentiation with respect over this element, this object, if you'd say it is an object. So what I will get? First, the differentiation will happen over conductivity if it is not constant, suppose. So that will be dou by dou x of k and dt by dx, dou t by dou x plus dou k will be out and it will be dou 2t by dou x square. Okay, dou 2t by dou x square equal to 0. So when you separate this equation into different parts, then you have what you have? There is a first order part of the equation and as well as a second order part of the equation, which you need to solve using the finite difference scheme, using the Taylor series expansions. Okay, so we have seen that using the Taylor series expansion, second gradient will come out to be phi I minus 2 phi I plus 1 minus 2 phi I plus phi j over del x square. Okay, for this part, and whereas here it was using forward difference or whatever you want, because FDM has not been discussed in detail. Phi I plus 1 minus phi I minus 1 over del x. Okay. So if you see, these two are separately treated in a finite difference scheme, and it is not giving you a conservative form of the equation. Whereas if you see for the finite volume scheme, you are integrating this term over a control volume all the time. You are not separating these two terms. That is why it is forming a conservative form of the equation. There is no Taylor series expansion happening here. It's just a control volume integration over the whole cell. So whenever there is a separation of the two terms, that means a non-conservative form. Whenever it is put it together, that is a conservative form.
Okay.
Okay.
Thank you. Thank you.
Yeah. Right. Now, coming back. So what I was saying about the Scarborough criteria. Yeah. Yes. Next, if we want to check that there is a boundedness property there or not, that whatever your solution is it bounded or not? So for that, what it is said to be that, suppose there is source is 0, if an equation source is 0, you have just an equation AP5P is equal to summation of neighboring nodes A and B, phi and B. So your solution is bounded or not. So what you will do, you will transpose this over right hand side, you will have the phi p's which will come at every point in the internal nodes 1, 2, 3, 4, 5, or at the bounded nodes itself. So you want to see that this all the points of the internal nodes from the boundary, suppose boundary is at 100 Celsius and 10 degrees Celsius. Your solution is bounded between this 100 to 10 degrees Celsius. So that will be A and B over A, P, phi of neighboring point, phi of the neighboring point. So boundedness is said to be that when you have a solution, and if you have a 2D domain, so if you have a 2D domain, suppose this is 300, this is 100, this is 500, and this is 400. So if you see that any point of time, this fraction is always less than 1, or it can be equal to 1. Okay, this fraction should be always less than equal to 1. That means that your AP should be always equal, try to be 1. So AP is equal to A and B to the maximum value, A and B up to the maximum value. So it can take any value between 100 to, it can take any value between 100 degrees Celsius to 500 degrees Celsius. That means your solution is always bounded. So neither you say it is less than equal to 1, just say that it is equal to 1. If it is equal to 1, then always your solution will be bounded. So for checking up the boundedness, the condition is A and B over summation of A and B over A, P should be equal to 1. This is your equality criteria, but Scarborough criteria is for convergence. That if your summation of A and B, mod of summation of A and B over the AP mod is less than equal to 1 for all the cells and less than 1 for at least one cell, then you are safe that your solution is converged as well. So we have discussed two properties here, convergence as well as boundedness. Is it clear? These two properties? So
So what is A and B, sir? You said AP is equal to A and B.
see, A and B is this now. This is the A and B.
The conditions for this one convergence.
Summation of neighboring nodes, na? West, east, north, south. I have said that NB is equal to east, west, north, south. That is A and B.
Right. Okay.
Okay. Now, okay. Now there can be different kind of boundary conditions for solving the solution. if you get the question as well. So what kind of boundary conditions can come? Boundary conditions can be like, one can be Dirichlet boundary condition. Y is given some C1 which is dependent over X. So that is kind of question is Dirichlet boundary condition of phi b which is dependent over X vector. This is a vector, not X direction only, X, Y, Z. Second kind of condition can be Neumann boundary condition, where directly the gradient is given, as we did in the previous question, where heat flux was given. Heat flux is nothing but k dt by dx. Gradient was given, and that was given to be some constant value. So that is Neumann boundary condition. Dirichlet condition we did last to last question, which was temperatures were given at both the ends. And there can be another kind of boundary condition as well, which is mixed kind of boundary condition. A phi plus B dou phi by dou n is equal to C3. So it has Dirichlet as well as Neumann. Gradient is also given as well as the value at the end is also given. Such kind of boundary condition is mixed boundary condition. Can you tell me like where can we apply them in the physical scenario where a mixed kind of boundary condition can happen? Can you think of a scenario?
What's your question, sir?
The question is, can you think of a real physical scenario where you will get a mixed kind of boundary condition? Dirichlet boundary condition we have seen, Neumann boundary condition we have seen in past two questions. But in what physical scenario a mixed boundary condition can happen, where both Neumann and Dirichlet is there? So we just saw in the previous question as well. If you think that there is a convection as well as conduction is happening at that same end, then that kind of boundary condition is a mixed kind of boundary condition, like in a fin case. Okay. All right.
Yes.
Just give me a second. Okay. Now let us solve one question as well, right? Taking one of the scenario of the boundary condition. Suppose with the for 2D, because just now we have just discretized this equation. Now we can solve as it as well, because in your assignment that is given, this that kind of question is given. So with the Dirichlet boundary condition I'm going with. First, Dirichlet. So if your cell is like this, this is your point of concentration. Dirichlet means at one of the boundary nodes it is given. So here directly phi b is given at the boundary. This is the one boundary node, phi b. This is your north. This is your east. This is your south. It does not have a west face for the left boundary. And remaining, you know that this is del x. This is del y. Del xc, del y. You know that thing. We have already discussed. So still I'll make this is del xe. This is del yn. This is del y small s. Okay. Right. Now you have framed the equation above only. So gamma EAE dou phi by dou x of east minus gamma WAW dou phi by dou x of west plus gamma NAN dou phi by dou y n minus gamma SAS dou phi by dou y s equal to plus some source term as well plus SC plus SP phi P del V equal to 0. Now if you observe that it does not have any west face, but you directly know, what do you know? For the west face, we know the B value. So if I write for the west face first, west face, because that is the boundary node. This is the boundary node. The previous equation was formed for, this equation formed for internal nodes. This is a special treatment for boundary node. So how you will write gamma WAW negative sign dou phi by dou x of west can be written as minus gamma, because it's a boundary B, gamma B AB for the west, dou phi by dou x of the boundary B. So that is nothing but gamma BAB linear assumption, that is phi P minus phi B over del x by del xB by 2. Del xB by, or del xB, sorry. I should write del xy and del xB by 2. This is nothing but del xB, this much. This is del xB. Whether it is half or not uniform or uniform, that is so far not our concern. And this AB can be written as, for this phase, AB will be how much? Area of base will be del y. Okay, del y into 1. Del y into 1. That is del y phi p minus phi base over del x. That is you have got for the west side. For the west side. Now you again put the values. Your boundary node has been solved. In the equation, rest east face, west face. The east face is you know, north face you know, south face you know, because those are not at the boundaries. All right. Any doubts in this?
No doubts, sir.
No doubt. Okay.
No.
Again, you will see the Scarborough criteria, that summation of A and B over AP is less than equal to 1 or less than 1 or not, and it is bounded or not. So for the source term, that depends. And that has been done by the prof in the lecture as well. I'm just giving you the brief. Now, if I take up with the Neumann boundary condition with you, Neumann boundary condition, same cell, but this time a gradient is given to you. So I'll just copy the figure. Copy, and I'll paste it here. is the figure here. Instead of this phi b, this time a flux is given here. Flux QB is given. Flux QB is given here. In normal modeling instead of that. So again, it is a boundary node. So again, the equation will be similar like this. Gamma E AE rho phi by dou x of east minus gamma B, the boundary node AB, rho phi by dou x boundary plus similarly for north, gamma and AN rho phi by dou y north minus gamma S AS rho phi by dou y south plus the source term, linear source term SC SP phi P del x del y equal to 0. Now it's given Neumann boundary condition. That means gradient itself is given to you. Gradient itself for this. Gradient itself is given to you. So what does that mean? The gradient Q, the flux Q at boundary node is nothing but minus of k dt by dx or gamma dou phi by dou x plus dou phi by dou y. So gamma grad of phi of the boundary node B, because flux definition is nothing but from the Fourier law of conduction. If you go with the Fourier law of conduction, that is nothing but k dt by dx. Okay, minus k dt by dx of dot with the I, which is nothing but minus gamma dou phi by dou x for the boundary B, So what you can write? You can directly write this circle term as q del y. You can write the circle term as here as gamma E AE dou phi by dou x east plus QB del y, because this AB was also there, na? So AB was del y into 1. Del y plus gamma n En del phi by del y n minus gamma s As del phi by del y south plus Sp plus Sp phi p del x del y equal to 0. This is your, again you will check for the Scarborough criteria and the boundedness by the way told in above. Okay, this is your Neumann boundary condition. Similarly, you can get a mixed kind of boundary condition as well. So mixed boundary condition is like there is a gradient which is being convected out of the, there is a gradient form. Suppose the fin question which we had, or you have a rod, there is a fluid flowing which is convecting, and here is some temperature which is being conducted. The fluid is flowing at temperature A, this temperature is maintained at B. Suppose this is a fluid is flowing at 100 degrees Celsius, this is at 80 degrees Celsius, until here some temperature it reaches to 20 degrees Celsius. So this fluid is creating a convection, and that convection is creating a conduction in that. So what kind of way it will take? I'll write it here. So this will be mixed kind of boundary condition, where there is convection which is balanced by conduction in the rod. So what you will write? The form of the equation is nothing but A phi plus B rho phi by dou x is a mixed boundary condition. And here you can write Q at the boundary is nothing but minus grad phi at the boundary dot I is equal to convect. It is being convected out of the fluid phi infinity minus phi b, which we did in the fin problem for 1D. Okay. And again, you can put the value. I hope this is clear so far. And similarly, this is a 2D. For 3D, what it will come? Here the equation is like 3D equation will be same. AP 5P is equal to A west, A east, A north, A south, A front, A back. Just one more term will also be added. And this will give you the three-dimensional equation. I hope is it clear? Just another dimension will add up, and the equation will be more or less same. And you can check out the lectures the professor has discussed about in very detail all these things for 3 dimensions. And 2 dimension, all the proofs have been done. I hope this is clear, or any doubts. Otherwise, we can end our session if you don't have any doubts.
No doubt, sir.
No doubts. Okay. All right, we can, I guess, end the session, and you can watch the lecture videos as well. So that will help you a lot to gain the confidence with all the derivations. Although I have tried to do as much as possible from my end for the derivation part and the questions. So, and you try to solve the assignment, that will help you a lot. Assignments. Even if you don't want to watch the lecture, after listening this tutorial session, understanding this, you can just go back and start doing the assignment. You will gain more confidence. Okay. Okay, I guess then we can end our session.
Yes, sir. Thank you, sir.
Okay, thank you.